This video is going to be about friction in two dimensions. So specifically, we're going to look at inclined planes and how friction behaves with an inclined plane scenario. So an inclined plane makes raising masses onto elevated surfaces a lot easier because you don't actually have to provide a force as large as the actual weight. So keep in mind the weight of an object is acting straight down. In order to cause something to go up, you'd have to provide a force that is at least equal to the weight before it will start to elevate. But if you actually put it on an inclined plane, you shouldn't have to provide as much force as the actual weight, and that even includes if friction is involved. So it's a lot easier to raise something if you have an inclined plane. The only problem with that is then you're working with trig. You're going to need to know the angle of the inclined plane, and for some it's a little bit tricky, but hopefully I break it down so it's simple enough for you. So inclined planes create a bit of an issue when you're on when you're dealing with forces. So keep in mind the normal force is always going to act perpendicular to the plane. So if you're at an incline of angle theta, then your normal is going to be perpendicular. Right, we're going to be perpendicular to that actual surface. But gravity will always go straight down. Gravity is always vertically down. Right, you can't get around that. So this creates a bit of an issue because therefore your normal uh, is not equal to gravity anymore, right? They're not in the same direction. Normal is now going to have a component that is going vertically up in the y direction. It's going to have a component that's going horizontally, in this case, left. So it has two directions now if I break it down to x and y. And the angle that you're going to have right here is your angle theta, right? It's going to be the angle of the incline. Now you can dissect the normal force, so that's an x and y, and that would be fine. Especially when it's something simple like this. But very often there's other forces involved. So it's usually a lot easier just to rotate the inclined plane and make gravity the force that has two directions now. So this is a rotated axis, and so we have the same idea that I just drew on with for the normal force, where we can break gravity down into two component vectors. But this time it's not in the x and y direction. This one is going to be working in something known as the perpendicular component of the weight and the parallel component of the weight, FG. Those equations, of course, are just component values. So given that your angle of your component vector triangle is theta, so whatever the angle of the incline is, your perpendicular component is just going to be your actual weight. So again, the weight is the hypotenuse, and hypotenuse is always the longest portion of the right triangle. It is a right triangle after all. So your perpendicular component is just going to be equal to your weight multiplied by cosine theta, as seen up here. And your parallel component, so that's the component of the weight that is acting down along the inclined plane. So it'd be the one that I would draw up there. Typically I draw up there. And that would be your weight multiplied by sine of the angle of incline, because again, we're using the angle that is right here. And so if you break that down, you can turn everything back into a seemingly up and down, left and right um, free body diagram. So if we look at it in this regard, we can see that the normal force is no longer just equal to the weight, it's now equal to the perpendicular component when there's no other perpendicular forces acting on the actual mass. And the force that's driving an object down an incline would be the parallel component of the actual weight. So this is you on a toboggan and you're on a hill. You're going to go down the hill based on the parallel component of your actual weight. So if we tie friction to the mix, and generally we don't draw all three of these. We don't draw the parallel, the perpendicular, and the true value of the weight. We usually just ignore that one and cross it off the list. But I didn't cross it off this one. So if we look at reality, there's almost always friction involved, but when in doubt, when it's just fundamental physics and we're just trying to get a general idea, we don't involve friction. But since friction's almost always involved, and assuming that we are going down and to the left, friction would be going up and to the right. And so one of the main reasons why we want to just rotate our axis is because then if we don't rotate our axis, sure enough, we have weight going vertically down, and that's fine. But then we'd have to consider that friction is therefore in the X and Y direction, and the normal force is in the Y and X direction. And so that just creates a lot more component vectors. So it's much easier just to rotate your axis and create component vectors for your actual weight. It really cuts down on the amount of work you actually have to do. So to summarize, when you rotate your axis, your weight is now going to be looked at in the parallel direction. So that is going to be your weight multiplied by sine of the angle of the incline. Your normal force will remain perpendicular, but if we're going to rotate your incline, then and your normal force is often just equal to your weight, because if you're on a flat surface, they're the only two vertical components. But now that we're rotated, then we have our normal force will probably be equal to your perpendicular component of your weight most of the time, which is now your weight times cos of the angle of incline, which means if we're on an incline, your friction force, which is generally your coefficient of kinetic or static friction multiplied by your normal, which is often just your weight. But if you're on an incline, it's going to be the perpendicular component of the weight, which means now your equation for friction is now your coefficient of static or kinetic friction multiplied by your weight multiplied by cos of the angle of the incline. So it just creates new equations. And so very often I skip stating these steps and just go straight to, well, I know my weight is mass times the acceleration of gravity, so I just go mg sine theta. Like same thing for my perpendicular component, I just go mg cos theta. And likewise for my friction, as long as I know there's no other perpendicular component forces, I would just say coefficient multiplied by mg cos theta. So I'll go through two problems, and hopefully I don't take too long to do that. Suppose you raise a 50-gram book on a piece of wood. We usually do this in class, and the angle is not quite 30 degrees, but go with me on this. Suppose you raise a 50-gram book on a piece of wood. The book remains still until you reach an angle of 30 degrees at the horizontal. What is the value of the coefficient of static friction? So you might have done this before. You raise an incline, and an object that you have on the incline doesn't move until you reach a threshold angle, and then it begins to slide down. You can actually figure out what the coefficient of static friction is just by raising it up slowly enough, just until you find that point where it starts to move. You'd have to do this a few tries just to get it so you find the exact angle, because sometimes the speed at which you go up, you're not really consistent, so you kind of go up and down, up and down, up and down, and ends up creating a jerking sensation, which is not going to give you a true coefficient of static friction. But alas, trial and error is usually how you do it in physics. So to start off, consider the forces that are involved. You've got your weight, and your weight, of course, is going straight down. So as far as your free body diagram is concerned, you would consider rotating your axis such that you are mainly dealing with your parallel and perpendicular plane. So perpendicular to the plane, your normal force will go straight up. So I didn't draw that on my plane here, but my normal force would go straight up in this direction. All right, so my normal force is still part of my free body diagram. All right, and my weight, it's not going to be straight vertical anymore. If I rotate the axis by 30 degrees, I'm going to be working with my perpendicular component of the weight. So the little subscript down there is pretty important. If I consider the parallel component forces, so often drawn horizontally to make life simple, I know the book would be at rest until I get to 30 degrees, which means friction is involved. So I'm going to draw friction going to the left because it's sliding down and to the right. It's sliding down to the right because of my parallel component of the actual weight, FG parallel. So in the perpendicular direction, I'm going to call up positive. I'm going to solve this once just so you can see how it's done. I do the same thing as I normally do. I just consider my net force is equal to the sum of all forces. And since this book is not going to fly off and suddenly go off in that direction, or suddenly break through the board in that direction, I'm going to just go on the whim and say that there's no acceleration. So therefore it's static. As far as the perpendicular direction is concerned, it is static. So there's no acceleration in that direction. All the acceleration is along the inclined plane. So therefore I'll make that equal to 0. So I've got two forces involved, one going perpendicular up, one going perpendicular down. My perpendicular component of the weight should be negative. So when I bring it over to the other side in magnitude, the normal force is equal to the perpendicular component of the weight. I will often just not even show this work and just go straight to this, because if there's only one force going up and one force going down and it's not accelerating in either of those directions, then your up is going to equal to your down. But if I had to show work, it would look like this. And if there was 3 or 4 forces in the vertical direction, or sort of the perpendicular direction or vertical direction, I would probably put those all into the equation and balance it out just like I did there, if it was a bit more complicated. So if I wanted to calculate my normal force, I'd just take the mass times the acceleration of gravity times cos of my angle of incline, and yeah, I'd leave it at that. So for the moment, I'm not going to plug numbers in. I'm just going to write that off to the side. I'll deal with the numbers after, because I generally don't like having to grab my calculator until I absolutely have to. So in my perpendicular direction, this is on hold until later. So let's move into my parallel direction. So in my parallel direction, I'd recognize that I only have two forces again. And the book is at rest. So let's go back to the question. It says the book remains still until you reach an angle of 30 degrees. So we're considering a static state. It is at rest until we reach 30 degrees, and that's when it begins to move. And so therefore we're looking for a coefficient of static friction, and when static friction is involved, then my net force is equal to 0. So in my parallel direction, my net force is 0. Once it does begin to move, kinetic friction will kick in, and then you'll probably have an acceleration. But I'm not looking for kinetic friction. I'm looking for my coefficient of static friction. So I'm going to keep it as a static state and make my acceleration 0. So the two forces involved in the parallel direction are your weight in the parallel direction and your friction, your force of static friction, if I put the S in there. Friction should be going in the negative direction, so when I take the vector symbols out, I will consider their actual directions. So my parallel component of my weight is going to be going in my positive direction, so therefore I just leave my parallel component positive and I make my friction negative. So therefore, if there's only two forces involved in the parallel direction, I can just say that going to the right is going to have to equal going to the left at the point where it is still static. So that means motion begins when my rightward acting force is just slightly larger than my force of friction. And so at that point, you more or less just make them equal, because then it's just an instantaneous, it can move or it can't move if they're actually equal. Most people would say that they would just begin to move. Wouldn't be a fast acceleration, but it would begin to move. So if I set them equal, and I've got my equation for my parallel component to my weight to be my mass times my acceleration of gravity times sine of the angle of incline. So that was the first few slides that we went through. And my coefficient, my force of friction is equal to my coefficient of static friction multiplied by my normal. And I've got the equation for my normal from looking at my perpendicular direction. I would substitute that into the equation. Now, again, I didn't calculate the number because I usually don't like having to punch numbers through a calculator. And for other reasons. When I plug it into this equation, I'll notice that I have the same terms on the left side and the right side. And so when that happens, you can actually just cancel them out. So mass and acceleration and gravity both cancel out on the left side and the right side because there's no other terms. I'm not adding or subtracting by other forces. So they actually just cancel out altogether, which makes the math quite a bit easier. So for that matter, I would just now isolate for my coefficient of static friction. Divide both sides by your cosine of the angle of incline. And if you recall from math class, hopefully you've seen this more recently. If you've seen it more recently in your math class, you'll probably remember it a bit better. But sine of the angle of incline divided by cosine of the angle of incline is going to give you the same thing as tan of the angle of incline. So that's just a trig identity. So, and you don't have to do this because you know the angle's 30. So of course you can plug in 30 degrees for there and you can plug in 30 degrees there. But if you know more information, it makes the math quite a bit easier. Plus you now have a cute little equation that'll give you the coefficient of static friction for anything that's on an inclined plane. If you want to discover at what what the coefficient of static friction is. You just raise something up until it begins to move, and then you can actually just calculate it by knowing that it's just tan of whatever that angle was. So that's just the real quick way of doing it, and there's your proof. So knowing that we have tan of 30 degrees, you just plug that in and you'd find out that in this case, the coefficient of static friction is 0.58 for this particular book for this particular surface. I know when we do this in class, the textbook that I have in class, the angle is usually somewhere just below 20. It's not always the same because I don't always use the same block of wood and I don't always use the same textbook, but this was just an example problem for the video. So I use 30 because 30 is generally an easy number to work with trig. Okay, so that's just one example using an inclined plane and friction. This one's just only slightly more challenging. So in this one, we have a 200 kilogram box and it's sitting on a ramp that makes an angle of 22 degrees at the horizontal. With what force do we need to push the box to start to move up the ramp? And we're going to assume that our coefficient of static friction is 0.4. So look at the scenario. We're going to push a box up an inclined plane. There's my little stick figure. I actually drew that. That's right, I am an artist. We've got an angle of 22 degrees and we're trying to go up the inclined plane. So we're going to provide an applied force in the red there going up the inclined plane, parallel to the inclined plane, ideally parallel. If you want maximum effort to get put into motion, you would go always along the inclined plane. We also know there's friction involved in the magenta color there, so that's going to be working against us. We know that gravity is going straight down, so therefore the weight is going straight down in the green. And of course, we're on a surface, so in the blue, we have the normal force. So that's just the main four forces that are acting on this mass while we're trying to push it up the inclined plane. So to put it in a free body diagram, a rotated free body diagram, so that way it looks like I'm always just working in the X and Y direction, but of course, because it's rotated, technically I'm working in the perpendicular and parallel direction. So in the parallel direction, I've got two forces. I've got an applied force, which we're going to say is going to the right, and my force of friction, which is going to be going to the left. I've got my normal force, which is acting perpendicular up from the surface. And then I've got my weight, which once I rotate, my weight is going down and to the left a little bit if I rotate this entire block down like this, 22 degrees. But as I said earlier, we generally don't want to work with your weight when it's not rotated. We break it down into a parallel and perpendicular component. So we break that one force down into two, and it makes our life a lot easier. Rather than having to break your normal, your friction, and your applied force each down to two forces, then we'd be working with 2, 4, 6, and then with weight, 7 forces rather than 1, 2, 3, 4, 5 forces. It does cut down the work a little bit. So in the parallel direction, we're going to start with the parallel direction because, well, the last example problem, I showed you that your normal force is just the same as your perpendicular, so we're just going to start with the parallel direction. We're looking for, once again, another static state. I didn't change it up and find a kinetics where we're actually going to accelerate. So that's just a different part of the problem. If it was going to accelerate, if we were using kinetic friction, then obviously Newton's second law would apply and you would just be having that equal to mass times your acceleration. But we're looking for how much effort force, applied force, do we have to put into the system just to get it to move. So therefore it's static in the parallel direction. So the three forces that are acting in the parallel direction are your applied force, your parallel component of the weight, and your friction force. So again, this is a parallel component of the weight, right? It's not in the X direction. Weight always goes vertically down in the Y direction. If you consider their actual directions, if I say up and to the right is positive, but when I rotate it, it's just to the right. My applied force is positive. My parallel component of the weight is going down the inclined plane, and my friction is going down the inclined plane as well. So one thing I really have to point out when you guys are solving problems, always remember that your parallel component of the weight will always go down the inclined plane. Friction is question dependent. So you might be pushing the block down the inclined plane and then friction would be going up the inclined plane. Right? In this case, we're pushing the block up the inclined plane and so therefore friction's acting against us and it's going down the inclined plane. but your parallel component of the weight will always go down the inclined plane. So please, 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 please always remember that. This guy's always going down the inclined plane, right? Down the inclined plane might not always be the negative direction, but it is in this case. But as long as you remember this guy's going down, we should be good. So in order just to cause something to begin to move, they say that your applied force has to be greater than or equal than your force of static friction. Forgot the S. But in this case, since we have two forces, one force acting in the direction of motion that we want, weight down the inclined plane is acting against us. So this weight would actually remove force from our applied force. So in order for this to actually begin to move, not only do we have to overcome our force of static friction, but we'd actually have to bring my weight over to the other side of the equation just for motion to actually begin. So your applied force has to do just that. When you bring both of these over to the other side of the equation, your applied force is going to have to be equal to your weight going down the inclined plane plus your force of friction just to initiate motion. So knowing that, we have a separate equation for your parallel component of the weight. We have a separate equation for your force of static friction, and I gave them to you earlier on. So there they are. I won't spend 10 minutes going through that again. Your parallel component of the weight is your weight multiplied by sine of the angle of incline, and your force of static friction is, of course, your coefficient of static friction multiplied by your normal, but there's only one force going up and there's one force going down perpendicular to the incline, so therefore our normal force is going to be equal to our perpendicular component of the weight. So if we solve for the parallel component first, we'd have your 200 newtons. Oh shoot, that's not newtons. Why did I write newtons? That's your kilograms. There you go, there's my mistake for the day. That should be kilograms. All right, kilogram box, mistakes happen. So you have your 200 kilogram box multiplied by your 9.81 meters per second square multiplied by sine of 22, because that's my angle of incline. And that should give us, I'm just going to scribble this out. And that should give us 735 newtons. Okay, so if you actually punch that through your calculator. So 200 times 9.81 should give you 1,962. All right, so you're going to need that number again because you need to calculate your perpendicular component of the weight. So when you calculate your perpendicular component of the weight, you should have 1,962. And again, oh, that bothers me. We all make mistakes occasionally. And so when you multiply those two together, you get 1,962 newtons multiplied by cos of 22 degrees, right? And that should give you approximately 1,819. I'm going to scribble this N out every single slide. Okay, so once you have your perpendicular component of the weight, that is technically your normal force, which means now we can actually calculate your friction. So plugging that into your friction equation. So we know our coefficient of static friction was 0.4. So we take our 0.4, we multiply by our perpendicular component of the weight, otherwise known as the normal force in this context, and you should end up with about 728 newtons. There we go. So the next step, now we've got our parallel component of the weight, we have our force of static friction. We can plug those back into Newton's second law. Normally, if this is my own personal work, I would have, in this step here, I would have just actually plugged in these two equations into my big equation there and there, and just would have done this all in one big step. But from what I gather, a lot of the time students prefer just to have the numbers in front of them. So there they are. So plug in those numbers in, 735 and 728, into my actual equation. All right, 735 and 728, when you add them together, you should get about 1,463. And if I'm following the rules of significant figures, then I'd probably just write it down as 1,460 kilonewtons. All right, so that's how much your applied force would need to be just to even begin pushing this block up the inclined plane. Right, but I will point out that even though we're going against the parallel component of the weight and against friction, it is still less force than actually lifting that block up. So this is the actual weight of the block, 1,962, or if I actually just read it out, your weight is 1.96 kilonewtons. All right, it's about 0.5 kilonewtons less effort to push it up an inclined plane, even against friction, than it is just to lift it up vertically in the air. So that's why inclined planes are very nice. We can move masses with less effort. So on page 40, you'll find a handful of questions. I would maybe do 10 and 11 before I attempt number 9, because number 9 is a bit of an ugly question because the applied force is not actually going up the inclined plane. The applied force is actually along the x-axis. So that creates a new dynamic to doing that problem. But I'm going to let you try to figure that out first and actually use your brain. Just use some of the information I gave you in this video and try to think it through. And if you do get stuck, I think I have this problem worked out and posted online. Otherwise, just ask me in class. But do attempt it first yourself and try to really think it through. And just as a heads up, if you remember that video and the lesson on weight and mass, sometimes things get combined together for quizzes and exams. Sometimes I love to just take all the topics and put them all in one big question and let you try to figure out how to actually do that. So foreshadowing, wouldn't be a bad idea to try to do that on your own too. So on that note, on page 40, try some of the questions and send me an email if you get hung up or stuck on something, or just, yeah. Okay, on that note, have a good one.